Completely away, please. Thank you. There you go. Power and efficiency. Hey, that's going to be on YouTube. The word power is used in a variety of ways in everyday language, but in physics, the word power has a very specific meaning. Power is how fast you're doing work. It's the rate at which work is done. Or it's the rate at which energy is transformed from one type to another. The faster you're transforming energy, the more power you're generating. It is a scalar. Screen is still frozen, Mr. Dewick. Let's do that. It is a scalar. You can underline the word scalar. I always forget to unfreeze the screen. As an equation, anytime I talk about the rate at which something is done, I'm dividing by time, so it's work divided by time. That equation is on your formula sheet. That's the last equation for this unit that's on your formula sheet. What are the units? Well, I guess it would be a joule per second. But we give this unit a special name. Power is measured in what? In watts. Symbol, capital W. Named after James Watt. I gotta be honest, I have a bias. I don't think he was that accomplished a science guy to have such an important unit that we use all over the place named after him. I wish they had named it after somebody else. Faraday would have been my preference, but it is what it is. So, if you are expending energy, say climbing stairs, it's not how much work you do that makes you feel tired, it's how fast you do the work. If you run upstairs, you'll be much more tired than if you walk upstairs, even though you've done the same change in potential energy, the same work. It's how much power you generate. In other words, power, not energy, not work, power is what leads to fatigue, to tiredness. If you do the work very slowly, you hardly notice it. This is how stairs and other ramps work. You expend the same amount of energy climbing the stairs, but the shallower the stair, the more time it takes, the less power you generate, the less tired you are. Example 1, a 60-kilogram girl runs up a flight of stairs 3.32 meters high in 2.6 seconds. A says, what's her power output in watts? Well, power is work over time. Hey, Taylor, what's the time in this question? Good. What's the work? Well, I think here it's going to be the change in potential energy. I think the work is mgh, right? Going against gravity. So it's going to be m 60, g 9.8, h 3.32 divided by 2.6. A standard flight of stairs is around 3.3 meters high. So like the stairs back there, they're both a little over 3 meters high. 2.6 seconds, that would be walking fairly casually up the stairs. You're not sprinting up the stairs. I picked these numbers on purpose because if we crunch the numbers, we get 751? 751 watts. I don't get why you picked those so carefully. Well, part B, the imperial unit for power, the imperial unit for force is pounds, the imperial unit for distance is feet, the imperial unit for power is horsepower, and it turns out 1 horsepower is about 750 watts. So what was her power output in horsepower? Little over 1 horsepower. Pretty much exactly 1 horsepower. In other words, if you climb a set of stairs fairly casually, that's about 1 horsepower. Nerd trivia, but okay. The horsepower was originally defined by James Watt. James Watt did not invent the steam engine. A lot of people think he invented the steam engine. He didn't. He improved it. What he really was a good salesman. This idea of inventing the unit called horsepower was brilliant. Because if you're going to a farmer, or if you're speaking to a factory worker and they've never seen a machine in their life, and you're trying to convince them that this machine can help them, you have to put it into a context that they understand. And so when he could say to them, this steam engine is 3 horsepower, the farmer thinks, oh, this does the work of 3 horses, even though it doesn't. Nothing to do with actual horses if you run the numbers, but it's a brilliant unit. How brilliant? We still use the stupid thing nowadays, even though none of us know how much work a horse can do in one day, but we still measure engines in horsepower. Ugh. Okay. Example 2. How long would it take a 5 horsepower motor to lift a 500 kilogram safe? You know what? I think lift is an important word here. I'll underline it. That tells me which force we're talking about. Up to a window 30 meters above the ground. Dylan, what's this question asking me to find? Okay. You know what? I have this equation here. Power equals work over time. That's got a time in it. Dylan, what's the T doing over here? How could I move this T over to the other side? So you're telling me I can do that? And how can I move the power over? Okay. So if I hear you correctly, you're telling me time is going to be work over power. Did they tell me the power? Well, yeah. They said the power is 5 horsepower. I can't use that. Dylan, what did I say about a paragraph earlier? What's 1 horsepower in watts? Okay, so I want horsepower to cancel. It goes on the bottom. I want watts left on the top. Remember this from Physics 11. 750 watts is 1 horsepower. I think a 5 horsepower motor, 3,750 watts. Double check me, but I think I'm right. Yeah. Okay. So it's going to be over 3,750. What about the work when I'm lifting something? What force am I doing work against? It's going to be mg, force times distance. Or if you want to think about it in terms of the work energy theorem, it's going to be the change in kinetic. That doesn't mention any change in kinetic. I assume we start and end at rest. And the change in potential, which is going to be mgh. It's going to be 500 times 9.8 times 30 all over 3,750. This is the fastest that this motor can possibly lift this safe up. $39.2 seconds. Replace motor and safe with, hey, express elevator. And you can say, okay, if I want the express elevator to cover the floors in this amount of time, how big an electric motor do I need to put on this elevator? Otherwise, you're out of luck. Oh, and this is also assuming, Prith, that this motor is 100% efficient. A motor that's labeled at as 5 horsepower, you're not getting 5 horsepower out of it. If it's labeled at 3,750 watts, you're not getting 3,750 watts out of it. You're not. But lets you know this would be some applications. You would like to know how long it takes you to accomplish certain tasks. It'd be nice if you could crunch that. Next page. There is a second equation for power. This one isn't on your formula sheet blatantly. It's hidden in the original equation. Work equals what times what? So I wrote here, power is work over time, force times distance over time. Kareem, all of us, circle the D and the T. Kareem, what do I measure distance in? What do I measure time in? So what I've circled is meters per second. What do I measure in meters per second? Speed, we'll go scalarville now, right? Speed. Another way to calculate power is if you know the force being applied and how fast the object is moving. That one's not on your formula sheet. How do I know when to use that? When they start talking about power and they don't give you a time, but they give you a force and a speed. Especially if they say constant speed, because then there's no change in kinetic energy. We'll look at an example of that in a second. But now we want to talk about efficiency. Efficiency is how much bang you get for your buck. It's how much useful work you get out as a ratio or as a proportion of how much work you had to put in. There is a symbol for efficiency. It's the Greek letter eta, which looks like a lowercase n with a long droopy tail. I didn't know that that symbol was the symbol for efficiency. I only found this out a few years ago. I always just wrote EFF as my abbreviation for efficiency, so I'll use both. But I have to admit, having a Greek symbol is kind of nerdy. So, what does efficiency equal? Well, it's power out divided by power in. What you get out divided by what you put in. Or work out divided by work in. Or energy out divided by energy in. And then tailored to make it a percentage, we times it by 100% because you'll get a decimal. Priya, I'll be honest, I don't memorize any of that. Here's what I know. First of all, if you're finding efficiency, make sure your units match. Make sure you're going joules divided by joules or watts divided by watts. Don't go watts divided by joules. That's the first thing. Secondly, I know the universe. In the universe, we can't ever be more than 100% efficient. It's impossible. That would violate the law of conservation of energy. So I know that this answer is always less than 1. So here's what I always do. This is what I've memorized. Make sure the units match, which makes sense. It's always going to be the smaller number divided by the bigger number, and then times 100 to make it a percentage. I say this, Prith, because sometime in your future, somewhere off on the horizon, you will be exposed to a question that asks you to calculate efficiency. And just the way the English is worded, in front of the power out, the word in appears. And in front of the power in, the word out appears. And every year I have some kid telling me, oh, this is 160% efficient. No. Now, if you do actually solve something, and it does end up being more efficient than 100%, you'll get a Nobel Prize, they'll name a unit after you. In about 5 years, you'll be able to buy Bill Gates, you'll have solved the energy crisis, you'll be the wealthiest person on earth. Sadly, ain't gonna happen. So I wrote down here, efficiency is always less than 100% unless you plan on winning a Nobel Prize. It'd be cool if you could find it. Ain't gonna happen. Prith is already planning. Well, what if you... No. Got to go on a light bulb rant. So, a typical incandescent bulb uses about 60 watts of power, 60 joules of energy every second. But incandescent bulbs are terribly inefficient. Where does most of the energy go into in an incandescent light bulb? You can burn yourself if you touch it. In fact, about 57 watts of a 60-watt bulb goes into heat. Only about 3 watts goes into brightness. And so, unfortunately, some well-meaning politicians who didn't have a good science background decided a few years ago they're going to ban incandescent bulbs. And they're slowly being phased out in Canada because they're inefficient. Yeah, but that doesn't mean you lose that energy. If the bulb is in a home, that person's heating bill is exactly lower by that 57 watts of heat. It's not wasted. It's heating up the room. Now, in the summertime, I will grant you, you probably don't want your room heated up. What country do we live in? Canada. In the northern hemisphere, yes? How does the lengths of our days compare in the summertime to the winter? Are our days fairly long? Are we using light bulbs as much in the summertime? I'm not sure there's really that worth the trade-off. Now, you might say, what about bulbs outdoors? they're trying to replace them with those spiral CFC bulbs. Those don't work outdoors where they don't deal with moisture very well. And those spirally bulbs have mercury in them. So first of all, little environmental note, because everyone does this and you shouldn't. Those spirally bulbs, please do not throw them in the trash when they burn out, because they'll end up in a landfill. The mercury will leak into the groundwater, and we at this point have no technology to get rid of mercury once it's in the groundwater. It ends up in the ocean. Seafood has been slowly becoming full of more and more mercury. It's why pregnant women are advised not to eat fish and all this stuff. We have no technology to get rid of it, and I don't know if we ever will, because mercury is that weird element. It's the one that's liquid at room. It's got some weird properties. So recycle them properly, first of all. The future is going to be LEDs, but they're still pricey. I'm slowly replacing, like, hey, they did my room with LEDs. Okay, they're really bright, I know. I'll tweak it a little bit. But they're very energy efficient. They give off almost no heat. And the only problem with them, these ones are pretty good. The standard bulbs, LEDs are directional. They point a beam of light in a direction, and for an incandescent bulb, you want it to go in all directions. So they're slowly improving the technology, but they're still pricey. Every couple of months, I'll buy a couple of new LED bulbs and replace a couple of bulbs in my house slowly. But I'm going to whittle away at it till the bulbs get to about $2 or $3 each, and they're almost there. Then I'll do the full replacement. So there's my little rant. For an electric appliance, the more heat it moves around, the higher its wattage. Your dryer is the highest wattage appliance in your house. In fact, if you pull a dryer away from a wall, you'll see it requires a special power outlet because it's requiring much more power than your standard appliance. All right, let's apply some of this. Example 3, end of rant. A 250 kilogram mass is lifted at a constant speed. You know what? I think constant speed is probably important. I'll underline that because that's one of those things I always want to take note of. Yes? Of 2 meters per second for a distance of 12.5 meters. A says, find the work done. B says, find the required power. And C says, if the motor is used... Okay, let's see what we got here. A. Work equals... Did they give me a distance? So I think I'll try force times distance. I won't look for a graph. There is no graph. I could probably solve this using change in kinetic and change in potential, but let's start with our simplest one. Which force when you're lifting? Oh, you know what? It is actually the change in potential energy in disguise. It's good old MGH, right? It's going to be 250 times 9.8 times 12.5. $250 times 9.8 times 12.5. I think this might work out nice. Oh, no. 30,625. I'll write down the whole thing in case I need to use it later. And then to 3 sig figs, 3.06 times 10 to the 4th. Work units, Newton meters or joules. No, but I would then I would write 30600. I'm just trying to get used to, I prefer my final answers on test to 3 sig figs. Okay? That's left over from the old provincial exam days. Lydia, what's B wanting me to find? So I wrote power, don't write this next bit down. In my head, I went work over time. I do have the work, 30,625. Do you see a time anywhere in this question? No. So here's what I did in my head. I said, I know that work, you can write this down, is force times distance. And then, Lydia, I circled the D and the T because that's meters per second. What is meters per second a measure of? Did they give me a constant speed in this question? Ah, this is how I can figure out power. Which force lifting? Which force when you're lifting? Even more basic. Yeah, you know what? It's going to be mg. I think the power here is going to be m times g times v. Okay. It's going to be m, 250 times 9.8 times 2. Oh, this I can do in my head. It's 500 times 9.8. 4,900? Double check me. Yeah? And power is measured in watt? I'll never get tired of that joke. Okay. Now, that's how much power we need, but it turns out that's not how much power this motor is rated at. This power is actually drawing in 10 kilowatts of electrical, you know what, should say electrical power, not electrical energy, but it's taking in 10 kilowatt, 10,000 watts. How efficient is it? Okay. Efficiency is smaller number divided by bigger number. It's power out divided by power in, and then times 100 to make it a percent. Watts and watts, because they gave me 10 kilowatts, so I'll use the 4,900. I'm getting out 4,900 watts of power. I'm putting in 10 kilowatts, which is 10,000 watts of power. Heck, I can do this in my head too. Oh yeah, times 100 to make it a percentage. It's 49% efficient. Where is the rest of the power? Where is the rest of the work over time going? Heat, probably, and sound. Especially gas motors, gas engines, internal combustion engines, they generate a lot of heat, and you could hear them from kilometers away. It's one of the advantages. In fact, I just saw last week, I think in the US, they've passed legislation. The new electric cars that are coming into the market, coming off the assembly line, they have to have fake noisemakers when they're going under 30 kilometers per hour because they're so quiet, pedestrians can't hear them. Blind people can't hear them. So when it's under 30, through speakers, I assume, some fake car noise is going to get piped out to make sure people who are visually impaired can hear that a car is coming. Once they're over 30, the electric motors are loud enough that I guess you can hear them okay. But you think about it, 20 years from now, when you see scenes in New York, right now, whenever I see a movie and the soundtrack is from New York, you always have all that traffic in the background and the honking. That might be a thing of the past. Traffic might be quiet. For those of you who live near busy roads, kind of cool. Also, if they're self-driving, the whole horn honking that you hear all the time on the New York, I watch it, but that might all be a thing of the past too. Who knows? Little nerd trivia. Taylor, up until now, this has been Physics 11. Let's get to some Physics 12 stuff. Let's combine different concepts. And in fact, I think in example 5, we're even going to do a lawnmower. Angle. Did I say angle? All that. All right. Taylor, what's example 4 want me to find? Power. Oh, you know what? I think, Taylor, I would underline a 2-word phrase. You know which 2-word phrase I would underline? Yeah. Okay. What do they want me to find? Power. Power equals. Now, Taylor, I know that power, if you need a tissue, the tissue's over there. Tissues are over there if you need them. I know power is work over time. Do you see a time in seconds anywhere? No. We're going to have to use that other definition of power, which said force times distance over time. Distance over time was speed. Did they give me a speed in this question? Yeah, I'm going to use this one. Okay, so it's going to be force times speed. Did they give me a force in this question? What else has this question mentioned that I haven't talked about yet in the second sentence? Friction? This is a job for a free body diagram. Let's do one over here. See how we're putting everything together now, combining different units, different topics? What are the forces acting on this mass? Get the obvious one. mg down. Is it sinking into the ground like quicksand? Is it flying in you like Superman? Normal force up. And I guess we are applying, or something is applying, an applied force to the right. By the way, that's the force that I want right here. It's going to be the applied force times the velocity. And friction. How big is friction going to be? Bigger, smaller, or the same size as the applied force? Is it smaller?
Same.
Why must it be the same? What 2 words did we underline? So what's my acceleration as a number? 0, which means the forces are, I'm looking for a word that means letter B. balanced. See how we put it all together? I'm going to say I like this question. I'm not saying I like. I'm just saying, hey, this is nice combining a whole bunch of different topics, putting a lot of stuff together. That's part of what we're trying to build more of in Physics 12. Physics 11, I had to keep the questions pretty straightforward. So I'm going to argue same size. Yes? Okay. Power is applied force times speed. I don't know the applied force. Oh, but look. I know another force that's the same size as the applied force. Friction. Power is going to be the force of friction times speed. Friction is what times what? Mu times the normal force times speed. I don't know the normal force. Oh, but look. I know another force the same size as the normal force. Hopefully we're getting now full circle, right? I think it's going to be mu mg v. That's how much power. Power is going to be 0.25 times 100 times 9.8 times 2. Really? You need a calculator? It's a 100 times table. It's going to be 200 point, let's go 25, 50, 490? Yeah. 490 watts. Okay. Cool. So this person is burning 490 joules of energy every second. I'm going to tire you out. Well, it's 100 kilogram mass. That's like 240 pounds. Yeah, you're pushing something pretty heavy across the floor. You're going to get tuckered out. Yeah, that would be tiring. Example 5. The key word here, lawnmower. Right away I'm thinking angles. Normal force is not mg. Components. I'm almost certainly going to do a free body diagram. So it says this. A person pulls on a 20 kilogram lawnmower with a force of 25 newtons, moves the mower 4.5 meters. The handle angle is 15 degrees with the horizontal, and mu is 0.1. Yeah, lawnmowers, the wheels, there's a bit of friction in the axles. They're not perfect. They try and make it as smooth as possible, but you can feel it, yeah. Okay. Cream, what does A want me to find?
Work.
More specific.
Work done by person.
You know what? Did they give me a distance in this question? So I'm going to use the definition of work, that's the force times distance one, and I'm going to argue it's going to be the applied force times distance. I don't know the applied force. You know what? We need to do a good free body diagram. Let's do one over to the right here, and I think I'm going to make it a little on the large side because it's going to be complicated. Okay. Kareem, what are the forces acting on this lawnmower? Get the obvious one. Yeah, I totally agree with that. And then let's do the weird one. Apparently we're pulling with 25 newtons at an angle of 15 degrees. Okay. Cream, is there friction?
Yep.
Yeah, and I think it's going to be shorter, although I'm not sure, but okay. Which one am I missing? Normal force. Is this a lawnmower? It's going to be weird. I'm not going to say look. In fact, is there an angle?
Yep.
What should I have done with that angle? Looking for a word that begins with the letter C. Yeah. Should have broken this up into Fx and Fy. And I think when you lift up on something, the normal force gets smaller. So I'm going to draw a significantly shorter arrow than gravity for normal force just to get my attention. Whew. Look up. Why would this be wrong? A deme. What? The force and the distance have to be in the same direction. Which force is in the same direction as the distance in my lovely picture there? Fx. You can write this down. Time to get tricky with it. Adjacent, hypotenuse, opposite. Yeah? don't know if you remember at the beginning of the year, I said you're going to get far better at trig than you ever thought possible. Hopefully trig has become almost boring and commonplace now. When do we get to next unit? Because we're going to be flogging the sine law and the cosine law. And you're going to get better at those than you ever thought possible, too. So non-right angle trig will become plug and chug. Which trig function is fx? Of cosine. In fact, you know what? I remember that I actually gave you another definition for work. I said it was the force times the distance times the cosine of theta if you have a force at an angle. It's going to be 25 times 4.5 cosine. It is cos. Remember that? So, how much work? It's going to be 25 times 4.5 cosine of 15. This one I can't do in my head. 25 times 4.5 cos 15. Because 25 cos 15 is fx and times the distance. You got 108.666. I'm going to write down 108.36s and a 7, and then I'll round off. 108.36s and a 7, and I'll round that to 109 powers measured. No, work, joules. Oh, good. That matches the answer that I have up there. Woohoo! Ethan, what does B want me to find? Oh, I think that's going to be the force of friction times distance, because they did give me a distance, 4.5. Ethan, friction is what times what? Times distance to make it work. I don't know the normal force. Oop, ugh. Okay. Ethan, is this a lawnmower question? Say yes. Because I underlined the word lawnmower. It's really what I mean is there a force at an angle? Yeah. Is it sinking into the ground like quicksand?
No.
Is it flying like Superman? That doesn't mean that normal force equals mg. This is complicated. It means everything down equals everything. Okay, what's everything down? Straight down in my free body diagram.
mg.
Good. What's everything up? Two things.
Fm and fy.
So the normal force is going to be mg minus fy. Right? Fy. Okay, trig function. Which trig function?
Sine.
You saw the sign? Okay. Well, normally I go of course I do, but we're doing a different order now, right? So, got to bring in something stupid. So it's going to be mg minus 25 sine 15. Okay, now let's plug that in way over here. This is going to be complicated. I can't say this is pretty. It's going to be mu bracket mg minus sine 15 times 4.5, where m is 20 and g is 9.8. You could do this all in one fell swoop if you wanted to type the normal force in first and then go mu times answer button times 4.5, whatever works better on your calculator. I'm going to go for the whole schmear because I'm a nerd. Mu 25? Oh, whoops. Thank you. Dylan, candy for you. 25 sine 15 times 4.5. Whew. By the way, we're going to go through the forces test either Monday or Wednesday. You're going to find that's a common mistake. Kids drop the mass magically for some, or the force magically, the coefficient in front of the trig. They're so proud of doing the trig right, they let their guard down. Mu, 0.1, bracket. 20 times 9.8 minus 25 sine 15. Close off the sine, close off the bracket times 4.5. Do you get 85.3? Why is that technically wrong? If you're not sure, go look at my answer up there in the brackets. Why negative? Because the force and the direction are in the opposite direction. We're losing energy. So you could either say 85.3 joules of energy lost to friction, or you can say, hey, negative 85.3 joules. Good yawn, Dylan? Good yawn, Taylor? Okay. What does C want us to find? Did they give us... Now, I thought about maybe trying to do this with work and energy, and then I went, wait a minute. Did they give me a distance? So I said, well, maybe I can solve this with kinematics with physics 11. Now, this question is worded poorly. We are going to have to assume that we start at rest. If I gave this to you on a test, I would include that in the description. I think if I can find the acceleration, I can use d equals vit plus a half at squared. Can I not? Put your phone face down, Kareem. Thank you. You're just staring at it. It's I know, it's an addiction. So by doing that, now you're back here looking up here. I know. And by the way, I don't blame you guys. Everything on your phones was designed by psychologists to be addicting to you. I'm not blaming you. That's why I do the airplane pie or put the phone away. I've learned if it's out of sight, it's easier, right? You okay with that? We could use d equals vit plus a half at. Now, how would we find the acceleration? Winner minus loser. Look at your free body diagram. Who's winning? Fx. Who's losing? Friction. What does that always equal? So we could find A, but I'm going to skip it. I am going to give you one of these to try in your homework as a nasty challenge. It's from last unit, so I'm going to make a dangerous assumption that you can figure it out because I'm losing you guys and it's tired and it's Friday and all that. So go to one more question here. Example 6. What's the first word of example 6? When I say nasty, what does that mean? Harder than I'm going to ask on a test. Probably harder than I'd ask on a quiz even. But definitely harder than I'd ask on a test. Says the person pushes with 85 newtons on a lawnmower. Hey, underline the word lawnmower. They're pushing down this time. I think the normal force gets bigger. I would do a good free body diagram. They give me a coefficient of friction. Did they give me a distance? Okay. And the mower starts at rest. They want you to find the final speed and the rate at which heat energy is generated. That's asking you to find the power due to friction. I'm going to skip this one. I am going to give you one like this in the homework just to see if you can figure it out. Understanding that that's purely to see if you can figure this out. What I do want to talk about, what I do think is fair game, is example 8. So, but you'll see one like example 6 in the homework. Because example 8 is a nicer application, more realistic. Stair climbers, exercise machines. Most of you at one point in your life or another will work out. On a stair climber at the gym, a 75 kilogram person lifts their center of mass. Lifts is probably important. That tells me which force we're doing work against. 22 centimeters. Ha! Nice try. Cross out the 22 centimeters. Meters, what is that? 0.22. Let's replace it right now. 0.22 meters. If they take 360 steps in 6 minutes. Ha! Nice try. 6 minutes. How many seconds? You really used your calculator for that? Are you kidding me? Are you kidding me? 360 seconds. And their muscles are 18% efficient. Then find, okay. Here we go. John, what's A asking me to find? No, read carefully the whole thing. The rate at which we do work. What's that a synonym for? Dylan. Power. Power. Which is work over time. John, it might also be the force times the constant speed. Here's how I know which one to use. Did they give me a time? Ha-ha! Oh, let's use that one. How much time? 360 seconds? 360 seconds, because I did it in my head. 6 times 60. You go 6 times 6 is 36, and you add a 0. That, yes? Good. Work. When you lift, when you're doing a stair climber, what's the work equation? What are you doing work against? Yeah, I think it's going to be the old change in potential energy, MGH. Okay. What is the mass? 75. G, 9.8. What's the height? It's not 22. It's not 0.22. Times 360, because in that 6 minutes, he climbs 360 steps times 0.22. And it's also divided by 360. You know what's kind of convenient, John, is the 360s cancel if you got the bottom part correct. So it's going to be 75 times 9.8 times 20 times 0.22. I get 161.7. I'll call it 162. Powers measured in watt? 162 watts. Not even close to a horsepower. Except that's only how much energy the machine required. This person actually burned far more energy, far more power, generated far more power than that, because you're giving off a lot of heat. So, what does B want me to find? The rate at which the person uses food energy. It wants me to find power done by the person. How efficient are they? Sit up. Okay? I haven't used this 18% efficiency yet. Efficiency is power out divided by power in. And I think this question, Kareem, is asking me to find that. So if I get power in by itself, I think I'll get power in equals power out divided by efficiency. How much power were we getting out? 161.7. I think it's what it was. Yeah. 161.7 watts. But that's only 18% efficient. How much power is this person actually generating when they work? This is why you actually get more bang for your buck when you're exercising, because your body is also giving off a lot of heat. You're burning a lot more calories than you realize. $898 powers measured in watts. Typically, an exercise machine makes an estimate for the average efficiency of a person, because athletes are more efficient than non-athletes, right? And so if an exercise machine is quoting you power or calories or anything like that, it is making a best guess. The calorie counters on those machines, the power counters on those machines are terribly inaccurate, but they're better than nothing. What's your homework? Show you what do I assign my block A's. So, 1, 2, 3, 4. Okay. 7. 8 is tricky. 8 is the nasty lawnmower question. So it's got a star next to it. If you can figure it out, I'll be impressed. 9. 10. 11 and 14. Really quickly, Ethan, can you read me? What did I assign? 1, 2, 3, 4?
1, 2, 3, 4.
3, 4,
7, 8, 9.
7. Put a star next to 8 because it's yucky, right? 9, 10, 11, and 14.
Yeah.
Thank you, thank you. Because this is the one that's going to go online.